We're going to look at the situation of dinitrogen tetroxide. We're going to go over a whole bunch of things here, and then as I go through the next few slides, we'll re-talk about those things. So the first thing we notice, let's look at the actual chemical reaction. We start off with dinitrogen tetroxide, and you'll notice that it's clear. There's a little bit of yellow in there because it's already started the reaction to make that nitrogen dioxide, and then as time goes on, it gets more yellow, and then it gets to like this dark brown, ugly color. And so we look and we start off in the concentration of NO2 is nothing, and we got the N2O4, and it's concentrated. And as the N2O4 goes along, it's going to be used up, just like kinetics. We could maybe figure out the rate law for that. And since it's being used up, NO2 is being produced. You see that that rate is quicker than it's being produced because there's that coefficient of 2. And so NO2 is going to be formed at twice the rate as N2O4 was used up. Nice little kinetics review. And so then we see that at this point, the concentration does not change. And so we've reached equilibrium. We know we're at equilibrium because if it wasn't equilibrium, then the N2O4 should be completely used up, and it's not. And so we write the reaction like this, where there's this double arrow saying that it's at equilibrium, versus this, which is what was going on at the first, because it was all going that way. It was all being made. And so there's a whole bunch of things we should notice about the graph. We should notice that NO2's concentration at the beginning was 0. We should notice that NO2's concentration increases. We should notice that N2O4's concentration decreases. When we get here, that they're both at a constant concentration, because no longer does that concentration change. It's important to note that since it's equilibrium, this is still being used up and this is still being made, but this is also being used up to make this. And so there's that equilibrium going on. And then if we looked at the rates, we would be able to find that, hey, the rates here is going to be equal to the rate of the other one. So it's not the best graph, but they'd be the same rate if we did rate versus time. So as I said, there's no nitrogen dioxide to begin with. At the beginning, it's only going in one direction because there's only one direction it can go. It can't go backwards because there was none of the product to reform into the reactant. The amount of N2O4 decreases and the NO2 increases, and there's a relationship in the rates at which this happen because of the kinetics and the balanced chemical equation. When they're at equilibrium, the concentration doesn't change, and so there's a horizontal line on the graph. The equilibrium is continuous, so it keeps happening. It's dynamic. It's not static. As I said, NO2 appears twice as fast as N2O4 disappears, and that's because of the balanced chemical equation. Also, this data is at a particular temperature, so if we change the temperature, we'd see a change in this graph, and we might physically see a change in color depending on how much NO2 was there versus N2O4 and so forth. So I think we have one more slide on this. As we talked about, as the brown NO2 forms, the color gets darker. At point C, it appears the equilibrium has been reached, because if we look at picture D also, those pretty much look the same. And then if we can look at the microscopic level, it's much more obvious that we're at equilibrium. I noticed those particles are in different places, kind of showing you that it's not the same thing going on, but it's a gas, so it's moving around. So maybe that's what it's just show you.